So today's flip tutorial will be on the technique of using partial fractions to integrate. Now before we start this section, I would like to introduce a small result because uh, this particular result will be very useful as it is an integral which will pop up quite often right during this section. Now if you integrate 1 over a linear function, so a linear function is something which has only x in it, no higher power of x, like say x plus b. And then the way to integrate this, of course, would be to use a U-substitution, right? So if you put u equals this denominator, we can show without much difficulty that the answer would be 1 over this coefficient right here times natural log of the full denominator, which is ax plus b. Okay, so now every time if you want to evaluate something like this, if you have to use the U-substitution, then it's going to take a long time. So what I would recommend you do is you remember this, right? And as a result, and use it freely as a result. So remember, if you have 1 over something linear, the integral of that would be 1 over the coefficient of x times natural log of the whole denominator. Okay, so for example, if you have 1 over 3x plus 2, if you want to integrate that, the answer would be, you look at the coefficient of x, which is 3, and you go 1/3 and the natural log of the full denominator plus a constant. Okay, now all right, so now so that's beside our main purpose of this tutorial. That's a useful result that we will encounter along the way. Okay, now first of all, when do we use this technique? Partial fractions are actually used to evaluate integrals whose integrands are rational functions. So what is a rational function? The rational function is one polynomial over another polynomial. So take a look at this integral right here. Look at the integrand. The integrand has one polynomial over another polynomial. Now if you have a square root here, then that is not a rational function because square root is not a polynomial. But right now we have a polynomial here and a polynomial here. Okay, so because if you distribute this out, you get x squared plus x minus 2, which is clearly a polynomial. So polynomial or polynomial, this is a rational function. So partial fractions means we will break it up into a couple of fractions and then integrate the fractions separately. But before you do that, not every rational function needs a heavy-duty partial fractions method, because as I always say, always the first line of attack should be the U-substitution. For example, if you have this integral, this is a rational function because we have polynomial over polynomial. But here, if you put u equals x squared plus 1, that will work because the antiderivative of u would be 2x, which is exactly the leftover part. Same thing here, if you put u equals x to the 4 plus 1, then the antiderivative is 4x cubed, which is exactly the leftover part. So for things like this, you don't need any heavy-duty partial fraction method. You can just use a U-substitution. But now let's take a look at this example. From example 1, let's look at this integral. Now, do we have a rational function here? Yeah, so number 5 is a number, but still you can think of it as a 0-degree polynomial. So we have something, and on the bottom we have a polynomial. So we have polynomial or a polynomial or a number or a polynomial. So that looks like a good candidate for a rational function. Now can I use U-substitution here? Well, if I call this u, right, then because it has an x squared thing, the derivative is 2x, but there is no 2x here at all, no, not even a single x, just a number. So you see that the U-substitution method will not work here. Then what do? What we are going to do is we are going to break this integrand into two fractions. And such breaking is called partial fractions. So what do? We take the integrand out and we break it into two fractions. How do we break those two fractions? First of all, we have some unknown constant which we have to find over something over the first factor, which is x minus 2, and then another constant over the second factor. Okay, so remember this is the integrand. The first factor is x minus 2, so we put something over x minus 2, one fraction. The other fraction is another constant over x plus 3, the other factor. Now, this is actually our first case. Now, we can only do this if the degree of the denominator is bigger than the degree of the numerator. Now, is that true? Because the degree of the numerator is clearly 0 and the degree of the denominator is 2. So, the degree of the denominator is bigger clearly than the degree of the numerator. And the other reason is that that has to happen, as well as the denominator must be a product of two non-repeating linear factors. So what do you mean by that? So look at the denominator. Do we have a linear factor here? Yes. Another linear factor here? Yes. So it's a product of two linear factors. And are any other factors repeating? No. So if we have this situation, when you have two linear factors that are non-repeating and the denominator has higher power, you can simply split it up as something over the first factor plus another thing over the second factor. This is the simplest case, but it is pretty frequent. So let's learn how to do that. So what happens if you have, say, quadratic factors and a repeating linear factor? Then the only difference would be the way we break up would be different, but we will do those things later. Right now we have two linear factors and they don't repeat. Okay, so then a over the first factor plus b over the second factor. Now what do we need to do? We need to find a and b, because we need to find what these numbers are, and then once we find the numbers we can integrate this. So that will be the integral of this and the integral of that, but the integral of this will be pretty simple because it's 1 over a linear factor, and the integral of this will be pretty simple because it's something over another linear factor, and we learned at the very beginning when we have 1 over a linear factor, right, we know how to do that, right? Okay, and that's very easy. So you can see the logic of breaking it apart into two linear factors, okay, because we know how to integrate linear factors. So this complicated mess becomes just 1 over linear factors. Okay, so here's the method. What we do is we take the full denominator and multiply out. Okay, so here's a full denominator x minus 2 times x plus 3. So we multiply the left hand side by that. Can you see that, right? Okay, we have to the left hand side. And then we multiply the right hand side also with that. Every term we multiply the first term as we multiply the second term. And when you do that, what's going to happen is you notice that on the left hand side the x minus 2 and x minus 2 will cancel off, x plus 3 and x plus 3 will cancel off, x minus 2 and x minus 2 here will cancel off, and x plus 3 and x plus 3 will cancel off. So the entire left hand side simplifies very nicely, and you only get 5 here, and then here you get what? A times x plus 3 plus what? B times x minus 2. Now here's what we're going to do. We have a and b here. Now we need to solve for a and b. So how do we do this? Well, if you can get rid of b, then we will only have a left. So if you want to get rid of b, what will be the easiest way of doing that? Because this is true for any x, we can plug in a certain value for x. So what is the value for x which will make b disappear? Well, if you put x equals 2, then we have 2 minus 2 which is equal to 0, and 0 times b is 0. So this will completely disappear if you put b equals x equals 2 here. So let's plug in. So likewise, if you want to get rid of a, then which should we plug in? If you want to get rid of a, we will plug in x equals negative 3. Anyway, let's first plug in x equals 2. Okay, so we plug in x equals 2. What happens is this whole thing disappears, 0, right? And then we have 5 is still on the left hand side, a, and x is equal to 2. So 2 plus 3 is 2 plus 3 times a plus b, 2 minus 2, which is of course 0. So this part is 0, and then this part is just 5a equals 5. So you have 5 equals 5a. And when you do that, you get a equals 1. Now we found a. Now suppose we want to find b, then clearly we need to get rid of a. So how do you get rid of a? We plug in x equals negative 3. So for x equal to negative 3, you get 5 is equal to negative 3 plus 3, which is 0. And here you get negative 3 minus 2, which is negative 5 times b. So 5 is equal to b times negative 5. So when you solve for b, you get b equals negative 1. So we have a equals 1 and b equals negative 1. So now we will plug back. So how do you plug back? Well, I mean, we can go up here and then we can plug back here. So a would be equal to 1. So we plug in a equals 1. So you get 1 over x minus 2. And then we have b equals negative 1. So we have b over negative 1 over x plus 3. So now we have got our partial fractions. Okay, so we plug in, we found a and b, and then we go up here, plug in for a, plug in for b, and this is what we get. Now we are ready to integrate. Okay, so then the integral of this would be the integral of this plus integral of that. So integral of this would be the integral of this plus integral of that. Now how do we integrate this? Remember, see, there's a linear factor here. Remember what I told you at the very beginning? A nice result you can use. If you want to integrate 1 over a linear factor, what you do is you go 1 over the coefficient of x times natural log of the full denominator. Okay, so can we do that here? Yeah, so we can go 1 over the coefficient of x. So the coefficient of x here is 1. So you can say 1 over 1, which is kind of ridiculous. Okay, times the natural log of the full denominator minus, once again, 1 over 1, which is again 1. Natural log of the full denominator, which is x plus 3. So really, well, 1 over 1 is meaningless, right? I mean, so you have the answer. Answer is equal to, we can just get rid of the 1 over 1, and then that is your answer. Now, usually when this question is asked, it is not asked like this, where the factors are neatly given. You will get a question like this, where you will have the denominator to integrate, say, 5 over x squared plus x minus 6. So the thing to do would be to immediately recognize that U-substitution will not work, and then that we need to use partial fractions and go ahead and factor the denominator. So the first step would be to go ahead and factor the denominator, and once we factor the denominator like that, then we can just break it up like this, and then the entire argument that we did will follow through, right? So break it up, first of all factor, and then once you factor it, write the two fractions as a and b, right? A over something and b over the first factor, b over the second factor. They multiply through what by the denominator, and then you get something like this. And then first get rid of one constant by plugging in a certain value for x, okay, and then solve for the other one, right? And then once you get that, right, okay, get rid of the other constant, okay, and then solve for the remaining constant, and then you plug back, and then you integrate piece by piece, and then you can use the result of it. Alright, so we have the video exercise is very simple. It looks just like the one that we did, except there's a slight difference. Instead of x squared plus x plus 6, we have x squared minus x minus 6. So break up the denominator and then write a over the first factor plus b over the second factor. Okay, factor the denominator and factors, and then find a and b, and then do the answer. So please bring the solutions for this video exercise to class on Friday. All right, that's it.